Hey Maurice, can you hear us now? Because Maurice left and then signed in again. Jasmine, we don't have a lab today. Lab will probably start Wednesday and Thursday, so we'll do it on Wednesday and Thursday. Maurice, can you hear us? That's my question. If you can, then we need to start the class. Wow, you say he cannot hear. What's the problem? Amalia, can you turn off your mic, please? Okay, I will have to start. We are recording the session, so I will take care of that. Hey, those who cannot hear us, I believe they can see what is happening. So I will have to continue.
Zico, maybe they can dial in using their phones. I know my anatomy teacher allowed some people to do that.
Or using their phone, and then so that the phone will act as for the speaker for them. If that's the case, then I have to give them the dial-in number.
Yeah, they wouldn't be able to see you, but they could hear you.
Let me see. And it's the anatomy teacher. No, I think I turned off the option of people logging in with the phone because I didn't want you guys to log in with the phone. Well, it's the first class, then I think we'll be able to fix it. We'll be able to fix it.
It could just be their internet connection, to be honest.
Okay, like I said, I will probably have to continue. Like I said, we'll try to adjust the syllabus to suit this. Concerning the lab, those who have questions concerning the lab, we'll be starting the lab on Wednesday and Thursday. And just follow up your Blackboard. We'll give you instruction on what you guys have to do with the lab. The lab will be during your lab time. That's what it is. So every instructor, every professor is required to teach or carry on his own activity during his normal class activity. This is to avoid conflict. If we have to start rescheduling, everybody will be rescheduling, and it might create, a huge chaos. That's why we need to maintain the same time schedule that we had before we went online. Okay, so Let's continue the class from where we stopped last time. Before we continue, I want us to go through this quiz. And it's not a quiz per se, it's, it's a QR time as usual. I want you guys to answer the following question. First question. Which of the following is not acceptable when drawing resonance structures? I want to see the response. This first question is compulsory for everyone. I want everyone to answer it because that's what I'm using to take my attendance. You will have to fill in your name before you answer the question. So I'm expecting answers from everybody.
Dr. Zico,
Yes, ma'am.
this is Adia. I'm on my way home to get on my laptop, but I've been in class on my phone. So are you going to do this again?
No.
Okay, well, can I let you know now that I'm still here, but I'm just headed home so I can get on my laptop?
You see here where? In school?
I guess on via Zoom. But yeah, I just wanted to let you know.
And the person who is driving, I don't know what the person is doing, mute his mic. I'm still following the response point, so that's why I'm a little quiet because I'm monitoring from here. I see what you guys are doing. Okay, guys, I will continue from here. So, which of the following is not acceptable when drawing a resonance structure? Okay, the first thing you need to keep in mind is that when you draw a resonance structure, only the electrons, whether lone pair of electrons or pi electrons, are allowed to move. So, A says move electron to sp or sp2 hybridized atom. That's totally acceptable. Okay. Now, positive charge are moved towards the electron. As a rule of thumb, positive charges are never allowed to move. Positive charges are never allowed to move. Only the electrons are allowed to move. So most of you answer B, which is correct. Okay. So part C says we're allowed to move electrons. Also, we'll never move atoms, so that is also something correct. Atoms never move. They stay, every atom stays on the exact position where they were. And so you can also move pi electrons. Okay. On the next question, I want us to go through a review question to put ourselves in the mood. That's the next question I want us to answer. Which of the following is not an acceptable resonance structure for I? Now, this I will not really require you guys to answer it. We'll do it together because we've spent 20 minutes doing nothing, so we need to move. So in this case, structure I will have all this resonance structure here. We need to choose the one that is not the acceptable resonance structure. And the hint here is not for you to draw out all the resonance structure. That's not the hint. The most important thing here is for you guys to be able to recognize some of the rules that govern resonance. Okay, if you look at structure A, B, C, and E, you will notice that all the atoms are exactly in the same position as that in structure I, except structure D, where this hydrogen has actually changed position. And in resonance structures, atoms doesn't move. But in structure D, you have an atom. The hydrogen atom moved from the oxygen above to the oxygen embedded in the ring. So D is a wrong structural resonance structure. Does that make sense? That's what you need to know in order to answer this particular question. The question I have from you is, which structure makes the largest contribution to the resonance hybrid? Which of these structure makes the largest contributor to the resonance hybrid? Again, we'll proceed by elimination. And by elimination, I will eliminate D and E from my choices. And the reason is simple. When I consider this particular oxygen atom here in D and E, when we consider that particular oxygen, what do you notice? You realize that the oxygen there will have 4 bonds, which is not possible. Oxygen will never have 4 bonds. The maximum number of bonds you can have with oxygen is 3. And when oxygen has 3 bonds, it will take a positive charge. So that's how we eliminate structure D and E. We've reduced our choices to A, B, and C. Okay. Now, if you compare structure A and B, there is one thing you will notice. The positive charge on this carbon here. Although that carbon has a positive charge, it does not obey the octet rule. You don't have 8 electrons around that carbon. How many electrons do we have around the carbon? I need someone to answer me. I will not be able to check immediately. So there will be 6. There will be 6 electrons around the carbon. Thank you. There will be 6 electrons around the carbon. So that's why A and B are correct. They are correct resonance structure, but they are not the best resonance structure. That's what I want to emphasize. A and B are correct, but they are not the best. D and E are completely wrong, are totally wrong. They don't exist because oxygen is having way too much electrons. Now, the best resonance structure here will be structure C. And structure C is the best resonance structure simply because all the atoms obey the octet rule. That's why C is the best resonance structure in this case. The next set of questions. This question actually serves as a review from what we've done so far. Okay. The next set of questions. Which of the following is the strongest acid? Which of the following is the strongest acid? In order to answer this question, we need to figure out which of them can actually generate enough resonance structure when you transform them to their conjugate basis. Does that make sense? And in this case, if you notice, A can never have a resonance structure. B also can never have a resonance structure. C can never have a resonance structure. Yes, question. Please, you will not be able to type your question because I'm not using the Blackboard window, so I will not be able to see your chat. If you have a question, just turn on your mic and then ask the question. Okay. Now, we have limited our choices to D and E. Between D, which conjugate base will have the most resonance structure? Between D and E. And I will guess D will be the one with the most resonance structure. Okay. Because we have two aromatic rings, it will be possible to delocalize electron between those two rings. So D will be our best choice. E will also be able to generate some resonance structure, but you will not have as many resonance structure as you will have in D. So D will remain our best choice. So D remains our best choice because we have so many resonance structure with D. Does that make sense, guys?
So are we trying to find the resonance structures of the base or the acid?
We give you the acid, but in order to determine the strength of the acid, you have to look at the resonance structure of the conjugate base.
Oh, okay. Thank you.
Yes, yes. The more resonance structure the conjugate base has, the more stable that conjugate base is, and the stronger the acid will be. Does that make sense? And so if you are not even able to form a resonance structure, like in A, B, and C, then your conjugate base will not be stable. And if your conjugate base is not stable, then your acid is weak. Okay? So these questions serves as a
Wait.
review.
Why couldn't A, B, and C form resonance structures?
You remember, do you remember the X, Y, Z that we use in class? X equals Y minus Z star. You know, in your structure, you should be able to recognize this component. And if you look at structure A, B, and C, you won't be able to see that. It's not possible. A doesn't have a double bond. B doesn't have a double bond. C doesn't have a double bond. So they cannot undergo resonance. Does that make sense?
Yeah.
Okay, so these review questions were basically to set the tone, to remind ourselves of what we did before we went on online. So we'll continue with the normal classes now. And I strongly believe that in class, this is where we stop. Okay. So today we'll be talking about electronic effect. Remember, all these things, we are basically looking at resonance and how resonance can help stabilize the structure. And once the structure is stabilized, how does it affect the property of the molecule? That's basically what we're looking at here. Okay. And now, one of the things we're looking here is what we call the electronic effect. And there are basically two types of electronic effect. Now, in the structure on the left, the first structure over here, Z is acting as our substituent. Remember what we mean by substituent. The substituent is any group that replaces a hydrogen atom. That's what we refer to as a substituent. So Z is our substituent, and Z can have two types of properties. Z can either donate electron to the benzene ring. In this case, we will refer to Z as an electron donating group. Does that make sense? So Z will be referred to as electron donating group if it donates electron to the benzene ring. And that is indicated by this arrow. If you notice, you see the arrow is going towards the benzene ring. It means that it's donating electron to the benzene ring. Okay? And usually, electron donating group destabilizes your base. Does that make sense? The electron donating group destabilizes the base, and it does that by increasing the electron density around this oxygen over here. Now, Z also can act as an electron withdrawing group. That's another property of Z. In this case, if Z is acting as an electron withdrawing group, will simply mean that Z is pulling electrons away from the benzene ring. And if Z is pulling electrons away from the benzene ring, it will consequently cause a decrease in electron density around that oxygen. Does that make sense? I want you guys to be able to picture that. If Z gives electron, if Z is an electron donating group, it increases the electron density around the benzene ring and the oxygen atom. Now,
So Dr. Zico,
yes, sir.
when you have those kind of like that, those branches that are right next to the Z, when they're pointing away from the Z, that means that it's pulling electrons away from the oxygen.
Like the first diagram, the one I circled, when you look at the arrow, what you call the branches, let me erase that so you can see better. Do you see these arrows here?
Oh, yes.
The direction of the arrow is going towards the ring. It means that we are donating electron to the ring.
All right.
Does that make sense?
Yes.
And over here, the next structure, the one I just circled, you notice that the arrow is going towards the Z. It means that Z is pulling electrons from the ring.
Okay, that makes sense. Thank you.
Yeah, and then remember, Z can be anything. Z can be a group of molecules. It can be a chlorine. It can be a methyl group. You know, it can be anything. Okay. Now that's the electronic effect. So, yes, question.
What is the base that it's talking about?
The base we're talking about is this oxygen. Remember, the base we're talking about is the oxygen. How does Z affect the property of that oxygen? That's basically what we're looking at.
Zico, I don't understand how the decreased electron density makes it more stable.
How the decreased electron density makes it more stable.
Yeah.
We are looking at the base. Okay, let me delete that and then let's try to do that again. Okay, so understand the stability. Remember that stability has to do with the resonance structure. Okay, now if we pull electrons, for example, the first diagram, let's focus here. How does that destabilizes this particular base here? What makes something basic? That's my question. That's the first question I want to ask you. How do you know what makes something basic? Can anyone answer the question?
When it accepts protons?
When it accepts proton, the ability to accept a proton, that's what makes you a base. Okay, that's what makes you a base, your ability to accept a proton. And now, if a base is destabilized, it means that that base can easily accept proton. Remember, stability means that you don't want to react. Does that make sense? Stability means you don't want to react. And in this case, reaction pertains to accepting a proton. And so if you are stable, you don't want to accept a proton. If you are stable, you don't want to accept a proton. If you are destabilized, you are ready to accept a proton. And you can only accept a proton if you have enough electrons. I don't know if that makes sense. If you have enough electrons, then you can accept a proton. Now, when you look at the first structure, we'll call this one structure A and call this one structure B. When you look at structure A, when the Z is giving electron to the benzene ring, the same electron will propagate through the ring and then reach the oxygen. So you see that the electron density around oxygen is increased because Z is donating electron. And so if the electron density is increased around oxygen, you are destabilizing the base, meaning that you are making the base ready to accept a proton. Does that make sense, Zaria?
Yeah, that makes sense.
Yes. So that's what we mean by destabilizing. So always think about destabilizing as being most reactive, in other words. That's what destabilize means. Okay? And so as a rule of thumb, what I want you guys to remember from this slide is that electron donating group will decrease acidity. In other words, if the acidity is decreased, it means that we are increasing basicity. Does that make sense? Basicity. Yes. Is that okay, guys? And if electron withdrawing group increases acidity, at the same time, we are saying that it decreases basicity. That's another way of looking at it. Does that make sense? That's the take-home message from this slide. So, there are two mechanisms in which electron can be donated or withdrawn from a ring. There are two mechanisms. The first mechanism is what we refer to as the induction or inductive electron withdrawal. That's the first mechanism by which electron can either be withdrawn or donated to the ring. And inductive electron withdrawal is simply the movement of electron through a sigma bond. Okay, and so when we have a nitrogen here, nitrogen is more electronegative than the carbon atom. Okay, and so because nitrogen is more electronegative, chances are that electrons will tend to move from the ring towards the nitrogen, because nitrogen is more electronegative than carbon. And so in this case, we'll refer to that as an induction withdrawal. That will be induction withdrawal. Another mechanism by which electron can move is through resonance. Electron can also move through resonance, which is what we've talked several times in this class already. Okay. For example, this is our original structure here. And we notice that a low pair of electrons on the oxygen can actually be donated to the benzene ring. We can give electron to that benzene ring. And by giving electron to the benzene ring, we're now able to draw all this resonance structure. So that's an electron donating group. So the methoxy group is the OCH3 group. So the OCH3 group in this case will be referred to as an electron donating group, and it donates electron through resonance. And when a group donates electron through resonance, we expect you guys to be able to draw all those resonance structures. So this would be a good challenge for all of you. I know you guys are able to do that because we've done something similar in class. So as a practice exercise, I expect you guys to be able to do this. So do that at your leisure time, and then we can always communicate and show that to me. I really encourage you guys to do it. Certain groups can also withdraw electrons from the benzene ring through resonance. Same thing. When we mean by electron withdrawing group, for example, the nitro group, NO2, is an electron withdrawing group. And we notice that the electron withdrawing group is pulling electrons away from the ring, as opposed to electron donating group that gives electrons to the ring. Take note of the direction of the arrow. With electron donating group, the arrow is going towards the ring. With electron withdrawing group, the arrow is going away from the ring. Does that make sense? And from there now you are able to draw all the possible resonance structures. And again, the most important, I will never emphasize that, the most important is to note that electron donating group decreases acidity and electron withdrawing group increases acidity, irrespective of the mechanism by which electrons are donated or withdrawn. Does that make sense? Whether electrons are donated by induction or electrons are donated by resonance, the end result is that so long as electrons are donated, the acidity will decrease. That's what I want you guys to keep in mind. So based on that, based on the ability of a group to donate electron or withdraw electron, we are able now to predict the pKa or the acidity of a molecule, which is the most important because that's the property we are measuring. We're measuring acidity. Okay, so over here we have a table that compares the acidity of a certain different types of phenol. Okay, I want us to pay attention only to the first half of this diagram here. That's where I need the attention to be. All those molecules are phenols. They are phenols because they have an oxygen, a hydroxy group connected to a benzene ring. That's what makes them phenol. And these phenols are acidic. They are acidic because the hydrogen connected to the oxygen can be donated. That's what makes it acidic. And in this case, when we measure the acidity, we're basically measuring the ability to donate the hydrogen. That's basically what the acidity is. The second thing I want you guys to take note here is the pKa values. We know how pKa affect acidity. The smaller the pKa, the more acidic. Does that make sense? The smaller the pKa, the more acidic. For referencing, I will label our structures again as usual: A, B, C, D, E, and F. Okay. From this structure A, B, C, D, and F, we notice that structure F is the most acidic. Structure F is simply the most acidic because the pKa is the smallest. Okay. And you can notice why structure S is acidic. Look at the substituent of structure F. The substituent here is the nitro group. And the nitro group is an example of an electron withdrawing group. Does that make sense? The nitro group is an example of an electron withdrawing group. And structure A is the least acidic. Structure A is the least acidic because it's connected to a methoxy group. And a methoxy group is an example of an electron donating group. Does that make sense? And so that confirms the rule. Electron donating group decreases the acidity, whereas electron withdrawing group increases the acidity. And so acidity increases in that direction. And now you guys will be able to tell me that the nitro group in this case is the most electron withdrawing group. Does that make sense? The same.
Dr. Zico.
Yes, Zion.
I know oxygen is more electronegative than nitrogen. So why exactly is it being the donating group?
Good question, Zion. So what do you expect? You expect oxygen to be an electron withdrawing group, right?
Yes.
Yes, that's a good observation. Now, in this case, there are two mechanisms that takes place. There is a competition. I don't know if the next slide we're talking about it. No, okay. Then I will mention it here. I will repeat Zion's question for you guys to understand. Zion is wondering why oxygen is acting as an electron donating group instead of acting as an electron withdrawing group because it's more electronegative than carbon. Zion, the answer is simple. Oxygen is an electron withdrawing group based on induction. If you look at the induction mechanism, oxygen will be acting as an electron withdrawing group because oxygen is more electronegative than carbon, and so the chances are that the oxygen will pull electrons from that carbon. But then don't forget, the same oxygen we are talking about also have lone pairs of electrons. Do you see that? With the lone pair of electrons, the oxygen can easily donate those lone pair of electrons to the benzene ring through resonance. And in this case, the resonance effect is dominating the induction effect. That's why oxygen behaves as an electron donating group instead of an electron withdrawing group. Does that make sense?
Yes, sir. So oxygen is going to kind of take some of the electrons from carbon, and then it's going to donate some of its own lone pairs to the ring.
Yes, and the effect of donating its lone pair to the ring overcomes the effect of pulling electrons from carbon.
Okay, okay.
Yes. Now look at structure D. Look at structure D, the one with chlorine. Look at structure D, the one with chlorine. So my question is this. Will you classify chlorine as an electron donating group or an electron withdrawing group based on what we have on the board here? The question goes for everyone. It's not just for Zion. I want to hear somebody else than Zion speaking. How will you classify the chlorine as an electron donating group or electron withdrawing group?
Chlorine would be the electron withdrawing group.
Okay, yes. I think I will have to classify chlorine as an electron withdrawing group. Now, coming back to Zion's question, remember that chlorine also has lone pairs of electrons. Okay, and chlorine is more electronegative than carbon. So chlorine will also have two mechanisms in competition: induction and resonance. But it turns out that induction is the one dominating here. That's why chlorine is acting as an electron withdrawing group. Because as an electron withdrawing group, the chlorine will be pulling electrons from the carbon through induction. And as an electron donating group, the chlorine can easily donate electrons to the ring through resonance. But because the pKa of chlorine is low, that is an indication that chlorine is more or less acting as an electron withdrawing group. Does that make sense? And with the same token, you are able to now use the same explanation to rationalize this observation, the observation in that change in pKa. You can use the same explanation to also rationalize the observation in this change in pKa. Does that make sense? The group connected with electron withdrawing group will have the most acidic group. So this carbon or this hydrogen there is the most acidic. Any questions so far, guys?
So is that because the chlorine is more electronegative than the oxygen, its inductive effect is stronger?
Say that again, Zari. I didn't get the question.
So if the chlorine is more like electronegative, is that why its inductive effect is stronger and it lets the chlorine act as an electron withdrawal group?
Totally correct.
Okay.
Yes, the answer is yes, yes, and yes. Because chlorine is more electronegative than the oxygen, that's why its inductive effect dominates its resonance effect. Yes, the answer is correct. Any other question, guys? I want everyone to participate. Let's make it participative. I don't want to be the only one speaking. So that's basically what I want you guys to understand here: the property, electron withdrawing and electron donating properties, and how that affects acidity and basicity of a molecule. Okay. Now, let's also see how electron delocalization affects the reactivity of a molecule. That's the next thing I want us to look at. The next thing I want us to talk about is reactivity. How is reactivity affected by delocalization? Okay. This is an example of a reaction we've done in class before. Reaction of HBr. We've done a reaction of HBr in this class before, in chapter 6, if you remember. And what we notice is that if molecule A reacts with HBr, it produces two molecules. I will call this one molecule B and molecule C. Okay. And what do we notice is that molecule B will be our major product because it is at 100%, and molecule C is the minor product, or molecule C is not formed at all at 0%. But when you look at the carbon here in the double bond, according to Markovnikov rule, both carbons have exactly the same number of hydrogen. So you should expect the product distribution to be 50-50%. Does that make sense? Because remember what Markovnikov rule says. The carbon with more hydrogen gets the hydrogen, and the carbon with fewer hydrogen gets the bromine. But in this case, because the carbon have the same amount of hydrogen connected to each other, they are supposed to form exactly the same number of products. But we observe something different. We observe something different. And so our job now is to be able to rationalize why we have that difference from the predicted product. We need to be able to rationalize that. And what would be the best way to do that, guys? What would be the best way to rationalize it? What do you need to look at? What should we do? You guys know it. I need someone here.
Do we look at the benzene ring and like the resonance from it?
Well, we can look at the resonance, but before that,
Whichever one forms the more stable carbocation.
which of the carbocation is more stable? That's what we're looking at. So we have to think about the mechanism. That's what I want us to do. So imagine this is our HBr here. So if we do the mechanism, the first step of the mechanism, electron attacks the hydrogen and then goes to the bromine. So once you do that, you will be able to form two types of carbocation. You will form this first carbocation here. I will call this A prime. And then you can also move ahead and form the second type of carbocation. I will call this A double prime. Do you see that? If you do your mechanism, there are two types of carbocations that could be formed. The blue carbocation called A prime and the red carbocation called A double prime. Now, observe those carbocations. You notice that the A prime carbocation is a secondary alkyl carbocation. It's a secondary carbocation. Whereas the red carbocation is a benzylic carbocation. Now, somebody else than Zion. I don't want to hear Zion again. Somebody else. I want everybody to participate. The second one is a secondary benzylic carbocation. In terms of stability, we already know that the benzylic will be more stable than the secondary carbocation. And that's why structure B will be our major product. Does that make sense? Structure B will be the major product because it goes through a benzylic carbocation, which is by far more stable than the secondary carbocation. And that's what this sentence is saying over here. Okay, and that's the reason why more of B will be formed and you will not be able to observe any C. And so we can rationalize again. We can use the same to study the reaction between isolated and conjugated diene. Okay. So let's look at the reaction of an isolated diene. 1,5-hexadiene. This is an example of an isolated diene. This is an example of an isolated diene because the double bonds are separated from each other by sp3 carbon. That's why we refer to them as isolated diene. And in this case, if you react those isolated diene with HBr, you will form that product. And this reaction simply follows the Markovnikov rule. Isolated diene are treated exactly the same way as monodiene, meaning that each of the isolated diene will react one at a time. You react the first isolated diene, then you react the second isolated diene. And what I want you guys to take note here is this reaction follows the Markovnikov rule. The two carbons involved here are the red and the green carbon. The ones are highlighted in red and green. And if you notice, the red carbon will have two hydrogens and the green carbon only have one hydrogen. So according to Markovnikov rule, more hydrogen will be given to the red carbon. Do you see that? And on your product, and on the product side, you notice that the red carbon ends up with an increased number of hydrogen. And then the green carbon will end up with the bromine. So that follows the Markovnikov rule. And you have to repeat the same process for the second diene. The carbon with more hydrogen ends up with more hydrogen, and the carbon with fewer hydrogen ends up with the bromine. So in this case, we don't have anything special to do. It follows the Markovnikov rule. And I expect you guys to be able to draw the mechanism. The mechanism is very similar to what we know. The electrons from the pi system attacks the hydrogen, and then the electrons between the hydrogen and bromine breaks and goes towards the bromine. You now generate your carbocation, and the carbocation is brominated. You repeat the same process with the second double bond, and then protonate the carbocation, and you end up having your product. Again, I will emphasize, don't just look at it. Go back and repeat this mechanism. Do it again and again. You remember what I told you guys in class. The best way to learn organic chemistry is to do it again and again. You can do it 30 minutes per day. That's the best way to study. It might look easy because I'm the one speaking, but I will highly recommend you guys to go and do it again. Does that make sense?
Are you still gonna upload the try your hand things on Blackboard?
Yes, I will upload some try your hand question. I will upload some try hand question, and I also want to let you guys know that office hours are available. The same way you connected to this Blackboard is the same way you will connect for office hours. So if you go, instead of selecting course room, you select the one that says office hours. I will be there, and then we can share screen, and I can see what you guys have done. Practice it on your own. I will give you guys some practice questions. I will really encourage you guys to do it. If you do it, you will not have coronavirus. That would be the best way to avoid having corona, by doing organic chemistry. Okay, so let's look at this isolated diene system. We have a different scenario here, guys. This is a different scenario. Let's look at the molecule A. You see that in this isolated diene, we have a double bond here and another double bond here. Let's call this double bond 1 and call that double bond 2. Now, I want you guys to notice the difference between double bond 1 and double bond 2. You will notice that double bond 2 is more substituted than double bond 1 is. Do you see that? Notice that double bond 2 is more substituted than double bond 1. And double bond 2, what makes it more substituted is the presence of that methyl group there. That methyl group makes that double bond more substituted. And so because the double bond is more substituted, that will be our most reactive site. So this double bond 2 will react first before double bond 1. And the reason is simple. The reason is simple. If we do the mechanism, I want us to think about it. Okay? I want us to think about it. If we do the mechanism using double bond 1, there are two carbocations that will be formed. The first carbocation will be CH2, C plus, H, CH2, CH2, CH3, double bond CH2. That will be our first carbocation. Then the second carbocation, if we react the other double bond, we will have CH2, CH, CH2, CH2. Do you see the difference between those two carbocations, the green and the red? What do you notice? I need an answer. I need to hear a voice different from that of Zion and Zaria. Please, somebody else should speak.
The red one is more stable.
Yeah, the red one is more stable. The red one is more stable because it's a tertiary carbocation. And because it's a tertiary carbocation, it means that it will react faster than a secondary carbocation. Does that make sense? And that's why this is our major product. That's how you can explain, you can rationalize that. because that goes through a tertiary carbocation, and so we have our more stable product. Is that okay? But then, if we change this reaction condition, and instead of reacting it with 1 mole, we decide to react it using 2 mole. If you react it with 2 mole, the first mole will react with this double bond, and the second mole will react with this double bond. So in this case, you will have a different product from what we have over here. In that case, you will have a product with a CH3 single bond and then a chlorine here. So that will give you 2 moles of reaction. That's what I wanted to emphasize in this case. Reaction of conjugated dienes. Now we have a conjugation. Double, single bond. Reaction with conjugated diene. So for this example, we are using 1,3-butadiene as our example. Now, from observation, we notice that when 1,3-butadiene react with chlorine, 2 types of product are formed, product A and product B. Product A is referred to as a 1,2 addition product, whereas product B is referred to as a 1,4 addition product. And our job, as usual, we need to be able to rationalize the formation of those products. Why do we refer to product A as a 1,2 and product B as a 1,4? The answer is simple. If you look at butadiene, this is carbon number 1, carbon number 2, carbon number 3, carbon number 4. And you simply notice that you've added the chlorine to carbon number 1 and carbon number 2. That's why it's called a 1,2 addition. With product B, you've noticed that your chlorine atom has been added to carbon number 1 and carbon number 4. That's why we refer to it as a 1,4 addition. Okay. The same is also observed if you react 1,3-butadiene with HBr. The 1,2 product means the hydrogen is added to carbon 1 and the bromine is added to carbon 2. That's why it's called a 1,2 addition. With the 1,4 addition, the hydrogen will be added to carbon 1 and the bromine will be added to carbon number 4. That's what is referred to as a 1,4 addition. Like in most reaction, that gives you 2 products. One of the product will be a major product and the other one will be a minor product. And so in this case, our job will be to determine which one is a major product and which one is a minor product. That's our job.
Zico, how come instead of doing a 1,2 addition and a 3,4 addition, it does a 1,2 and 1,4?
If you do a 3,4 addition, it will be the exact same thing as a 1,2 addition. Does that make sense?
Yeah.
A 3,4 addition is exactly the same as a 1,2 addition, just that you're looking at it from the other end. So our job will be to determine what are the conditions that will favor the formation of a 1,2 product and what are the conditions that will favor the formation of a 1,4 product. What I mean by that is what condition will make the 1,2 more the major product, and which condition will make the 1,4 more or the major product. Does that make sense? That's what we're looking at here. Okay, and so if we're looking again at a detail, this is still a nomenclature between 1,2 and 1,4. Then what we are naming here, we are only focusing on our conjugated system. That is carbon 1 of the conjugated system, carbon 2, carbon 3, and carbon 4 of our conjugated system. Okay, and if you look at the structure of 2,4-hexadiene, this is what our 1,2 product will look like, and this is how our 1,4 product will look like. To better understand this product, what you need to do is to go down and write down your mechanism. Everything starts from the mechanism. That's what I'm emphasizing again. This is why mechanism is important. Everything goes from the level of the mechanism. And so, if we want to look at the mechanism again, that's why I emphasize to you guys to practice your mechanism. I will never emphasize that again. I will keep saying that every day. Now, if you study your mechanism, the first step of the mechanism is a familiar step, what you guys know how to do. And when you do the mechanism, you form your carbocation. This is my carbocation. And what I notice from the carbocation is that it is an allylic carbocation, meaning it is an X, Y, Z carbocation. Do you see that? Because it's an XYZ carbocation, it can undergo resonance. And so if it undergoes resonance, it will produce this second carbocation. Does that make sense? So we now have two types of carbocation. We have carbocation A and we have carbocation B. Those are the two types of carbocations we have now, A and B. B is formed as a result of resonance, whereas A is the first carbocation that was formed. Does that make sense? And now, if we go down, we notice that the bromine now can either add to this positive charge. If it adds on that carbocation, it leads to the formation of this product, the 1,2 product. If the bromine connect to this carbocation, it leads to the formation of that product, the 1,4 product. That's how you can rationalize the formation of those two products, the 1,4 and the 1,2. Does that make sense, guys?
Dr. Zico,
Yes.
how could you tell between the 1,2 addition and the 1,4, which one is more stable?
That's a good question. That's the next question I was about to ask you guys. You know that. You know I will always ask this kind of question. That's why you asked it before. Which one is more stable, product A or product B? That's my question. I need someone to answer it.
Product
A.
B.
A.
A is more stable.
I will go with B. Wait. Hold on. It looks like I can make a pool. I can make a pool here. Just give me a question. You remember that we are still experimenting with this stuff, right? We're still experimenting this stuff. So I will create a poll here. Which one is more stable, A or B? First choice A, second choice B, and then start. Can you guys see that poll question? Yes, I like it. This is fun. This is really fun. Remember that all these polling questions like that, they will be acting as my, how do we call it? As my attendance. Having the question correct or wrong does not affect, but it will be acting, it will be counting towards the attendance point. So even if you don't know the answer, just answer it because I will use that as my attendance. We're still waiting on about 9 people to answer. We still have about 9 people. Okay. 6. Let's see. Show responses. So those are the responses. 6 people didn't answer, and then most of you guys are going with A. Most of you are going with A. I will, let me see. Okay, let's get back to the question. Most of you said A, to be the more stable. Now, it depends. That will be my question. That will be my answer. It depends. But when we talk of stability, we're looking at the thermodynamic stability. In this case, B will be the most stable product. B will be the most stable product because you have a more substituted double bond. Remember, the more substituted the double bond is, the more stable the alkane. So that's why the 1,4 product is a more stable product. A is not the most stable because this double bond has too many hydrogens connected to it. The fewer the number of hydrogen, the more stable the double bond. That's why B is a more stable product.
Dr. Zico.
Yes.
So are we just always supposed to look at the double bond when it comes to conjugated diene stability?
But in this case, this is no longer a conjugated diene. A and B are no longer conjugated diene. Look at the product A and product B. They are no longer conjugated. Do you see that?
Yeah.
Yeah. So that's why B is more stable. Now, let's look at the carbocations. Let's come back to the carbocation. Okay. These are the carbocations here. Oh, well, let me highlight them. These are the carbocations. We have carbocation A and carbocation B. You all will agree with me that carbocation A is more stable than carbocation B. Does that make sense?
Why?
Can somebody answer the why? I need someone else to answer the why. Shelby, answer the why. Or I don't know, whoever should answer the why.
Because B is a primary carbocation.
Because B is a primary allelic, whereas A is a secondary allelic. So A is a secondary allelic. It means that A is more stable than B. Does that make sense? But in terms of product B is more stable than product A because product B has a more substituted double bond. Now, in the next slide, or in a couple of slides that we'll look at later on, we will say that A is called the kinetic. In the next slide, we'll refer to A as the kinetics product, and then we'll refer to B as the thermodynamics product.
Dr. Zico.
Yes.
How do you know that you're supposed to look at the double bond to determine stability for this one?
For the product, always look at the double bond. If I ask you which product is more stable, always look at the double bond. The double bond that is more substituted is the more stable. Does that make sense? And for the carbocation, you already know the order of stability for the carbocation.
So when you're trying to find out which one's the major or minor product, are you supposed to be looking at which one has the most stable cation, or do you look at the stability of the product?
Now, your question, the answer to your question is this. The major or minor product is not necessarily the most stable product. Does that make sense?
Somewhat.
The major or minor is not necessarily the most stable product. Major or minor depend on your reaction condition, and that's what we'll be doing next class.
Oh, okay.
Yes, the first slide, this slide here explains what we'll be talking about the stability of the carbocation. Okay, one carbocation being more stable, like this carbocation is more stable because it's secondary, and this one is less stable because it's primary. That's what this slide is talking about. But in the future, we'll now be talking about kinetics and thermodynamic product, and that is where you will notice that the most stable is not necessarily the major product. A product could be kinetics or a product could be thermodynamic, depending on the reaction condition. And that's what we'll be talking about on Thursday. Does that make sense?
Yes, thank you.
So I will want to know, I will post a link with the poll on Blackboard. it will just to know your satisfaction with this online experience, because it's the first time we're all doing this. So I will ask you a couple of questions, and I really want you guys to answer it. It will be like multiple choice question, just to have your feeling, how you felt about this first experience, and what are the kind of things that you think we need to do in order to make the class look much more better and stuff like that. Does that make sense? And participation of everybody is encouraged, please. It's really necessary for us. We didn't plan for this thing, and every input will be necessary to make our experience fruitful. Okay, so any question?
Is there any way that you can make it like more interactive so that we can kind of do the work also, like more polls?
Like doing more polls, okay? Yes, I will do that. I will have to incorporate more polls so that everyone we can participate more.
Will you still be posting the lectures, like on YouTube or whatever?
Say that again.
Will you still like be posting the lectures so we could go back and rewatch it?
Yes, I will be posting the lecture. I was recording the lecture, so I will post it.
Are you planning on changing the homework dates?
I changed the homework dates already.
Okay.
Yes, the homework dates were changed. I think the deadline now are the 27th for both homeworks.
Are we still going to be having Blackboard quizzes?
Say that again.
Blackboard quizzes, are we still doing that?
Yes, you still have Blackboard quizzes.
So when you eventually give out the test, it'll be online, right?
Like I said at the beginning, it depends. Watch out with your email. If the school decide to extend your stay, then I have to figure out a way to give you the homework, to give you the exam online. But if you guys have to return on the 3rd, then we'll have to do an in-class exam. So just watch out with the email, okay? I will keep you guys posted.
Okay.
Okay, see you guys. Bye-bye.